Now let's talk about experimental designs and methods. So far, when we've talked about random assignment, we've talked about what's called a completely randomized design. In this design, treatments are assigned to experimental units completely at random. Random assignment tends to balance the effects of uncontrolled variables so that differences in responses can be attributed to the treatments. So we had 24 plants, and we randomly assigned 4 plants to each treatment, and at the end we'll maybe take the average number of tomatoes per plant in each treatment group and compare to see which one gave the best yield. But sometimes we want to reduce variation even more when we have a known variable that we cannot control for. So you can also do what's called a randomized block design. The experimental units are divided into subgroups called blocks, similar to strata when we do sampling. Each block shares a common known variable that, one, cannot be controlled. In other words, we can't equalize it among all the treatment groups. Or we cannot make just that variable equal. For example, like we could make sure each plant got an equal amount of water, for example. But there are some variables that cannot be controlled. There's some differences in those plants that we know about, but we can't do anything about. Those are variables that we might want to consider for blocking. Now, how do we know whether or not we should block? If that variable is likely to affect the response variable. After blocking, then treatments are randomly assigned within each block. So, for example, in the original experiment, there was a variable that we knew about that we couldn't do anything about, and that was the store that the plant came from. So blocking by store, putting Lowe's plants in one block and Menard's plants in another block, would have been a good way to deal with that situation. So here's another example. Let's say Miss Thumb could only find 12 plants of one type of tomato, so she has to buy 12 plants of one type and 12 of another. She knows that different varieties of tomato plants may naturally produce different numbers of tomatoes, so she decides to use type of tomato as her blocking variable. Okay, so the blocks then would be 12 plants of variety A and 12 plants of variety B. Notice that within the block, the plants are the same for that characteristic. Once you have the plants divided into blocks, then you proceed like we did with the 24 plants. You're going to randomly assign plants to treatments. Since there are 6 treatments and 12 plants, we're going to randomly assign 2 plants to each treatment. Now, afterwards, what's helpful about the blocking variable? Well, we could determine the average number of tomatoes per plant in each treatment group and compare. This would allow a comparison between treatments and as well as between tomato varieties. After comparing varieties, then you could also combine all the treatment 1 plants into one group, all the treatment 2 plants into one group, and so forth, and having 4 of each treatment, and then compare treatments, knowing that you have an equal amount of variety in each group, so any difference in yield caused by the tomato variety affects each treatment group equally. Of course, the random assignment still distributes unknown sources of variability as evenly as possible within the groups, but having only 2 plants per group means that any differences between individual plants could strongly influence the tomato yield in a group. So replication is a bit of a problem in this particular scenario. Now there's one other type of blocking that's kind of a specialty type of blocking. It's a special case of randomized block design. Using a blocking variable, subjects, whether they are people or not, are arranged in pairs matched on relevant factors. Sometimes you might block on several different factors, but you want to match up 2 of the subjects as closely as possible on those variables. So matched pairs may be formed naturally, like for example, identical twins are matched pairs, or having 2 of the same kind of plant might be matched pairs. Or the experimenter might group together subjects that are similar in some way. Every pair receives both treatments by randomly assigning one treatment to one member of the pair and subsequently assigning the remaining treatment to the second member of the pair. Alternately, each subject may get both treatments, and we'll talk about one of those examples later. This method is best for experiments with only 2 treatments. So let's say that Miss Green and Thumb found out that pruning really helped her tomatoes. Now she wants to see if pruning is equally beneficial for other varieties of tomatoes. She purchases 2 plants each of 6 different varieties of tomatoes, all at the same store, so store is not an issue. Each pair of plants of the same variety form a 2-plant block called a matched pair. They are matched because they are the same in a way that might affect the response variable, which is tomato yield. So variety 1 are a pair, variety 2, and so forth. Now, she's now going to prune one in each pair and not prune the other, but that has to be still randomly decided. So make sure to randomly assign which plant in each pair gets pruned, perhaps by tossing a coin. Number the plants in each pair 1 and 2. If you toss a head, plant 1 gets pruned. If tails, plant number 2 gets pruned. Not every experiment involves blocking, but it's helpful in any case where you have a known variable that you think might influence the response variable. So what is the main purpose of blocking? The main purpose of blocking is to reduce variation caused by other variables, so that the variation in the treatments can be seen more clearly. And I will highlight that in our next example video.